Okay, we already did that one. 9.2. Number 14. Yes, it's an arithmetic sequence, an arithmetic sequence, because D is equal to -3. Number 40, your first 5 terms were as easy as 200 and then subtract 10 over and over and over. 190, 180, 170, 160. Number 48 was nice because they gave you the first term and the last term. You multiply that by the number over 2. It doesn't matter that it's odd. It still works out just fine. Number 54. Was arithmetic. Common difference was +4 because you're adding 4 using the first term and the common difference. Whoa, 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 whoa. N was 50. How are you guys supposed to figure out the last term for your partial sum? Because you need the first and the last. Yeah, you don't want to add 4, add 4, add 4 49 times, right? So we needed the 50th term. The easiest way to get there would have been using the equation to say, hey, take -6 and add 49 jumps of 4. There's your 190. Now you have your first. Now you have your last. Solve, solve, solve. 66 is D and 68 is A, and I think those are all the evens. So look in front of you. Do you have any odds you want to ask? Yeah. 63. Yep. Period 2 didn't like that one either. Oh, hey, you guys have the exact same questions today. Anything else? All right, go team. Here we go. Number 45. That was really nice, too, because I didn't get their recording to work out so well. Oh, my goodness. This guy. Okay. Let's go back to the end of section 9.2. The nice thing is we didn't even really need to do that word problem, huh, guys? Because I don't think you guys really got stuck on any of that type of problem in homework. Here's our number 45. Let me grab number 63, which I think is right. There he is. All right, number 45 is our first one. You guys can tell they gave us a sub 1 and a sub 2. They gave us the first term and the second term. They told us it was arithmetic. Pretend I didn't just cross out the important part that we're supposed to be looking at. If it's arithmetic, what's my common difference if I know the first and second? Yeah. So my common difference, I just need to subtract. What am I trying to find? The 7th term. Well, guys, whether you have the formula memorized or you're trying to memorize, or whether you're just trying to figure out the pattern, how do I get the 7th if I know every time I'm adding 2.4? How many jumps will I go from the first? From the first, 6 jumps of 2.4. And that should end you at your final answer of 18? I did it too fast. 0.6? 12, 24, 14. Oh yeah, 14 and 14 is 18. Good. Dun, 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 dun. Does that make sense? Okay. Number 63. Now, could you have just plugged it in your calculator? Honestly, yes. How do you think they you to try to solve it? By hand. And by hand, I'm not going to plug in 1 to 500 and add them all together. No way, Jose. But I will go ahead and start plugging in and figure out 1 plus 8 is, 2 plus 8 is, 3 plus 8 is. I think I see a pattern. Yeah? When's it going to end? Plugging in 500, right? So plugging in 500 will get me 508. Why do you think I left a few blanks? What would have been right before 508? And then 506. Why am I reminding you of this? What did little Gauss figure out that we're going to steal and use for arithmetic sequences? Add the two together. And let's double check. What's 10 plus 507? What's 11 plus? Same thing. So how many 517s will I have? How many? No, more than 30. Isn't it S sub 500? Don't have to add together all 500 terms. Does that make sense? So then what's my n over 2? Yeah, they're going to be 250 5/17ths. Right, I'm just going to box it, but that would have been your final answer. Does that make sense? So yeah, you could have plugged it in your calculator, but if it was by hand, you would have definitely wanted to do it this way and find the pattern. First plus last, let's do 250 of those and we're done. Cool? Any more questions going once? Yeah. It's all based on the recursive formula they gave us. So the recursive formula, remember, shows the jump. And so to get to the next term from the previous term, we have to subtract, which is possible with arithmetic. You could also see like plus and negative 10. That would also make it go down. But every time you go, like for instance, when you go to the second term, that'd be 1 plus 1. You'll get the first term, which is 200, and just subtract 10. So you're just going to follow the minus 10, minus 10, minus 10 pattern. Does that make sense? Yeah. Okay, anything else? Going once, going twice, and sold. 9.3. Guys, grab out your calculators if you don't already have them out. Just because there are a couple discovery-ish things that we're going to go through today. But first of all, we got to play around with this nth partial sum formula a little bit more. So let's play around with this nth partial sum formula just a little bit more. We started playing with it yesterday, which is super good. So we're like a whole slide ahead of period 2. Go team. Is anybody else kind of warm? It's kind of stuffy. It's been going back and forth today. It's like super cold and super warm and struggle. All right, here we go. Kiddos, with this example, could you have just thrown that in your calculator? Yes. How would you do it by hand? I would say this, except some of you are realistically thinking, I don't want to do what by hand? What's scary in this? 12th power, you got to be kidding me, right? Okay, so would this probably be a non-calculator problem on the test? No. But there might be a problem similar that has a much smaller exponent that you could do by hand. Does that make sense? I'll try to do another example like that in just a second if we don't get one that is practical to do by hand. Number 56. Yes, I know you could throw the sum in your calculator, but remember, we're doing a lot of intro stuff, a lot of background stuff, working towards hard calculus problems, and let's just say their problems aren't as easy as plugging this in a calculator. We'll just put it that way. Okay. So let's think through the by hand way of dealing with this guy. Does he look exactly like that? Not really. I mean, this guy did. There was something times something to the power of I minus 1. This one just has something to the n minus 1. Now, maybe some of you are like, wait, I think I could make it work. But if worst comes to worst, you can always just plug in. What's 1 minus 1? And what's 0 power? Okay, so it starts at 1. Then what's the next one going to be? Plug in 2. 2 minus 1 is 1. Plug in 3. 3 minus 1 is 2. If I square 3 halves, I get 9/4. I'm going to put a dot, dot, dot. When does it all end? Plug in 10. 10 minus 1 will be 9. Am I going to raise this to the 9th power? And the answer is no. But that's what we would do. Is this a geometric series? Series, yes, there's addition. Geometric, what do you guys think? What's it take to be geometric? Okay, some of you guys might be realizing there are always exponents in the nth term formula. You're not totally off. That is usually true. Actually, it's always true. You have to be careful it's not anywhere else also, though, or else you could get in trouble. But then geometric, don't they all, I mean, it said geometric. We know it is. So Trevor was like, yeah, hey, there's an exponent. But also, what's going on as we go from one term to the next? Yeah, there's a common ratio. And the common ratio is 3 halves. So how do I plug into the S sub n, S sub 10? Why did I choose 10? Good, the top bound is 10. How do I plug into that formula? What goes first? Careful, not 3 over 2. And this one, your very first term is 1. Does that make sense? And if you want to think about it, some of you said there's nothing in front. Well, there was something in front. Who was in front? So there's 2 ways of looking at it. 1 was in front, and who's in front is your a sub 1. But then also, when you expand your series, 1 was the first term. So that's a sub 1. What comes next? 1 minus, right? So 1 minus 3 over 2 to the power of 10 all over. Am I going to do this one by hand? Probably not. Probably not. To the 10th power is really nasty. But you're learning how to use the formula. You're learning how to use the formula. So we would plug that into our calculator and solve, solve, solve. We're going to see what these decimals are in just a moment, but first of all, let's go ahead and look at number 72. How is this one different than either of the other 2? It's not in a nice summation notation. It's all written in its like original series notation of like, hey, there's the first term, second term, third term. But we kind of have to figure some stuff out by ourselves. So, stink, guys. It is geometric, but what's my common ratio? Some of you might be like, oh, but it's minus 8, minus 8. Oh, it doesn't work. It's not arithmetic. How can I find the common ratio? I need to divide. Remember at the very beginning of the section how we take a term and instead of subtracting, now we need to divide? So r is going to equal 24 over 32. And you'd have to reduce that, but it end up being 3/4. Is that easy to see, 3/4? As long as you make your fraction, yes, right? But what happens if you don't make a fraction? That's really hard to see, right? I don't go around thinking about what it looks like to multiply by 0.75. Like, I can cut things in half. That one's easy. But cut things in 3/4? Ugh. Anyway, so my r is equal to 3/4. That's how I'm going to multiply to get from one jump to the next. But what's the dilemma? Do I even know what my n is? I know what my a sub 1 is. He's right there, 32. Go team. I have my a sub 1. I have my r. But who am I supposed to be finding? They want me to find this entire sum, and to find this entire sum, well, stink. I'd have to figure out who n is. Even if I was trying to use summation notation, which is what they say, so I could be trying to use the snazzy, like use a sigma, make I equals 1 to n, and say, okay, no big deal. I know that a1 is 32. I know that my common ratio is 3/4. But even in summation, I can't solve until I know who. Ugh. Well, who's this guy? He's my n. But how do I find n? Yeah, there are 2 ways. One way is very logical. One way is, couldn't you take 18 and say times 0.75 times 3/4? See what it is. Times 3/4 again. See what it is. Times 3/4 again. See what it is. Eventually, what should it land on? And you could count and see how many more jumps. That's like a very critical thinking, easy way of doing it, right? But Rachel said, why don't you take the nth term and set equal to? Hand down. Too much temptation. Why don't you take the nth term and set equal to? So what's the formula for the nth term for geometric? All right, let's use it. Zach, you were saying it a second ago, right? A sub n is equal to a1, which is 32. Keep going. Which is 3/4. I don't know what n is, but who do I know? What's a sub n? What's the nth term in this one? Solve. You got this. Algebra, right? Get n by itself. Just a couple of you will get stuck really fast, though. For my ones that are already stuck, we don't like the n up here, right? That's nasty. But hold on. Did everybody divide by 32 first? But once we divide by 32, for anyone who's stuck, how do I get to that n? Logarithms. I would love to take a square root, a cubed root, a fourth root, but I don't know what that is. I can't take a root. I don't know what kind of root to do. So the only way to do it, to break it down, is a logarithm. Because a logarithm has that really cool property that powers can go where? In front. So I can rewrite this to be ln of 10.125 all over 32 is equal to n minus 1. Someone help us out. What would be the next step? If we don't care about how nasty it is, we're going to our calculator anyway. What would be the next step? Inverse. An inverse operation. And the operation I see that needs to be undone is multiplication. So how do we get rid of multiplication? Yeah. If I'm not scared of how nasty it is, it's going in my calculator anyway. Well, whatever, just divide ln of 3/4, because then don't you just get n minus 1? Nice. How do I solve for n? Okay, let's see if you can get it in your calculator. Can you get it put in nicely? It should be a nice even number because n just stands for first term, second term, third term. It should be a nice even answer. As you guys are doing that, my numbers got kind of big and messy. Let me make this a little bit nicer so it all fits on one screen. Nice. You guys agree? Good. Now, I mean, look at the math, kiddos. If you were allowed to use your calculator, it was a multiple choice answer. Why would this probably have not been the smart way to go? How quickly would this have happened? Super soon. You had the third term. Times 0.75 would be something a little bigger. Times 0.75, you were done. You're like, oh, hey, it's the fifth term. Okay. But what if n was equal to 19 or 25 or 34? Ugh. We wouldn't want to find that by hand. That would be really nasty. Okay. I want you guys to go ahead, and since you're in your calculators anyway, can you go ahead and either use the summation feature? To believe it or not, some people in period 2 who tried the summation feature actually got it wrong because they plugged it in wrong. Just be careful. You can either plug in the summation feature or you can plug in the fraction. I want you guys to find both of these decimals for me. They're nasty. We wouldn't do them by hand because to the 12th power and to the 10th power, ugh. It'd be a little too hard. But let's find the decimals. And let's think. This series starts at 4 and multiplies by 0.3 a lot of times. And this series starts at 1 and multiplies by 3 over 2 or 1.5 a lot of times. My question is, which one's getting bigger faster? Both of them are adding. Both of them are adding on, adding on, adding on, adding on. Most of you would say like, oh, if it's adding forever, that'd be just getting bigger and bigger and bigger and bigger. But is that really true? Who has the first one for me? 7 what? Got it. If it started at 4, it's gotten very big. Still kind of close to 4. I mean, it's 5.7, so it's getting close to 6, but it hasn't gone very far. Can you guys change the formula just a little bit? And instead of going to 12, can you go to 50? Instead of going to 12, go to 50. Let's see. Okay, maybe we just need some more jumps. Maybe it's going to get bigger. What's S sub 50 going to be? Whether you plug in 50 here or whether you plug in 50 there. Ooh, 5.71. Stink. Christina, do you have both? What were some more decimals here? Yeah. What were the ones down here? there have been an additional 38 jumps. This guy isn't going anywhere very fast, right? I mean, he went up from 4 to 5.7, but then he's slowing way down. Is he still adding stuff? Yes, but how big are each of the things that are being added? Pause. Can you guys just do 0.3 to the 12th? 0.3 to the 12th. How big is that? Times 10 to the power of? -7. Ooh. So this guy, it's like 0.00000. Is it adding anything very big? No. Now, as it keeps adding smaller and smaller and smaller, guess what? The growth slows and slows and slows. And so for all practical purposes, this one, I could even go to infinity. Have you guys go to 100, to 500, to 1,000, to 5,000. It's still going to be 5.714. The decimals will kind of stabilize, is what we would call them. And the number just kind of settles. Does that make sense? Just kind of settles into one number. Let's see what's different with this guy. What happened when you guys plugged him in? The 10th partial sum, whether you plugged in the summation or whether you plugged in the formula, what'd you get? Oh, is that for the whole thing? Sorry, for the whole thing. I think it's 100 and something. Yeah. 113.330. Did anybody do the 3 over 2 to the 10th, though? What would be 1.5 to the 10th? Let's see, what on earth? This guy went from 4 to 5-ish to 5.7-ish. This guy went from 1 to 113? What's 1.5 to the 10th? Do you see the difference between this one that's going to 57 point something and this one that's going to 0.000000? What's the difference between this common ratio and that common ratio? One of them's above 1 and one of them is below 1. What happens if you raise 1 to really high powers? 1 to the 50th, 1 to the 10th, 1 to the... just stays 1. So 1's boring. He doesn't do anything. He doesn't get smaller, he doesn't get bigger, he's just kind of there. But can you guys check in your calculator? What's 0.9? Let's do something on the less than sign. What's 0.9 or 0.99 to the 50th? Does even that get smaller? It's so close to 1, though. What's 0.9 to the 50th or 0.99 to the 50th? Zach, you have it. 0.6. What's 0.99 to the 100th? .3. Is it getting smaller still? Now, it's taking longer. 0.3 got smaller way faster, but still, anything less than 1, when raised to higher and higher powers, will always get smaller, and the number for geometric will always stabilize. Now, why don't you like 1.1? Not 1.5, just 1.1 to the 50th. 1.1 to the 100th. So close to 1, but what's 1.1 to the 50th? 117. That thing's growing. What's 1.1 to the 100th? Who has that? Whoo! See, just one little baby tenth above shows a lot of growth, or a possibility for growth, but 1 teeny decimal below. Now, wait a minute. Why am I talking to you guys about all these things? This one just said find the 12th. This one just said find the 10th. This one just said find, I don't know, this guy. Okay, the 5th. We figured it out eventually. Which we figured out what n was. Did we even finish the problem? I don't think we did. How would we have finished the problem on this one if it asked us to find the sum, not just find n? Where would we have had to go with this guy? Yeah, we would actually have to plug in 5 to be the top bound there, or we would have plugged in 5 into the S sub n formula. So we would have just taken this guy, and we would have said, now we know our upper bound. Now we know our n is 5. And guys, what do you think you're going to expect on this guy since there is a 3/4? Do you expect it to go way high? Or do you expect it to be kind of like, not so far away? Yeah, not so far away. Now, the numbers are a lot bigger. You're starting at 32. So the numbers are going to be big, but they're not going to be growing so large like you saw up here as far as being so far away from where it began. So you guys are plugging in. You can plug in either to this formula, plugging in a 5, or plugging into this formula, plugging in a 5. And our final answer, just so we can finish this guy and move on, is Hold on. I have a calculator. I promise. It might work if the batteries are alive. Which way are you guys doing? The summation way or the formula way? Summation, yeah, it's kind of faster. Where are we going? 5? Ooh, we'd have to make our little formula, but that's okay. We already wrote it down. To the power of. Okay, what'd you guys get? Did I beat you? I did. You silly goofs. We're just being quiet. Do you agree? Uh-oh, don't agree? I just plugged it in that one because it was faster. Not bad to be quiet, as long as you're still awake. And know how to use your calculator. Are we okay? Okay. I wasn't just staying with 12 or staying with 10. I was having you guys go to 50 and go to 100, and here's the reason why. Didn't you already start taking notes on this? What's the top bound in that guy? Infinity. Uh-oh, I think we have to grow. Hey, what was I having you guys do with the bounds? Wasn't I having you guys grow the bounds? I was having you take bounds of 10 or 12 and go higher to 50, go higher to 100. I was having you approach, in a sense, infinity and say, I wonder what's going to go on as n gets higher and higher and higher and higher. And what does infinity mean? Growing and growing and growing and growing, getting bigger and bigger. It's not an end. It's more of like a direction. Infinity just says, oh, keep going. Okay, fine, I'll keep going. So we just saw when the common ratio is greater than 1, it's just going to keep growing and growing and growing. There won't be a sum. There won't be any bounded value that it won't go past. It's just going to keep on growing. Now, it's a snazzy way of writing it. The absolute value of r is greater than 1. Another way of writing it is you could say if r is greater than, put the or equal to. Because if it hits at 1, it's really boring. It doesn't shrink, and so as such, when you keep adding, it will keep growing also, just in a very different way. The sum, the partial sum will. The absolute value says, hey, this works for positive numbers greater than or equal to 1. This works for negative numbers less than or equal to negative 1. Whenever the magnitude of the number is bigger than 1, 1.1, negative 1.1, 1.5, negative 1.5, there will be no sum, no infinite sum. But if r, like you guys saw, is something less than 1, and it works for negatives too, so greater than negative 1. Any of the numbers that are 1/2, negative 1/2, 3/4, negative 3/4, 11/12, negative 11/12. Any number, positive or negative, that has a magnitude less than 1, not greater than or equal to, the sum will exist. Technically, a snazzy term for this first one does not exist. We would call it a divergent series. Not like the book series or the movie series, but divergent, the idea is still kind of there. It diverges from any set answer. It diverges from any set sum. Whether it goes to positive infinity or whether it goes to negative infinity, whether the sum grows positively or grows negatively, or whether the sum can't make up its mind and oscillates. Divergent, it's not getting closer and closer to any sum. It's dying. This one, you guys have this formula written down, right? I think my light bulb is burning out. Hang in there. Let me turn off the light. I think it's the warning. Fix a light bulb. How do you fix a light bulb? Yeah, exactly. We need to get one from facilities. Okay, you guys have divergent and convergent, right? So here's the idea. I'm going to go ahead and white out this little S sub n. Can you guys erase the S sub n? And we're going to write it in a calculus way. That is so gnarly. Oh, you know what? My monitor is doing that too. Hold on. It's not the projector. It's my monitor. Ew. Maybe it's the cable going out? Oh, it's the cable going out. All right. For right now, we're okay. We can't plug in infinity. Remember, you guys in section 9.1, you were all thinking, like, where's the infinity button in your calculator? And I was like, there is none. So instead of plugging in infinity, we are going to go ahead and approach infinity. So the infinite sum, are we using i's? I like n's better. We'll use i's. Okay, fine. I equals 1 to infinity of whatever we have, a sub I. Since we can't plug in infinity, what we can do, snazzy calculus notation, is we can take the limit as n goes to infinity of s sub n. That's just a cursive L, limit, L-I-M, shortened notation for limit. We're trying to ask ourselves, does this sum have a limit? Does it have some sort of boundary it'll never pass? Does it have some sort of number it'll stabilize towards? And to do that, we take the limit, don't worry, I'm not teaching you all the calculus today, but the idea of I can't plug in infinity, so I'm going to have the n go towards infinity. So I'm going to have that part of this formula go towards infinity. And s sub n's formula is a sub 1 times 1 minus r to the n all over 1 minus r. And as we talked about, if r is less than 1, greater than negative 1, and we did examples of it, what's going to happen as you keep on raising those 0.3s, 0.75s, 0.99s to higher and higher powers? What's going to happen to this little piece right here? It's going to get smaller and smaller and smaller and smaller, 0.0, 0.00, 0.0000, 0.00000. This piece is going to go, just this piece, it's going to approach, using that arrow again, 0. But that only happens, that only works if r is in between 1 and negative 1. That only works when r is in between 1 and negative 1. If r was 1 or negative 1 or anything bigger than, this is going to go to some sort of infinity. It's going to expand. And if it expands, well then there is no set limit. This is just going to get bigger, 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 bigger as you keep adding, 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 or subtracting, subtracting, subtracting. But if r is in between these two ranges, as I raise him to higher and higher powers, he gets closer and closer to 0. We say the limit exists because the n is out of there, and all that's left is, well, everybody else. And who's everybody else? A1, 1, no 1 minus, because 1 minus 0 is just 1, and then 1 over r. So could you memorize this? Yes. But you need to know when it works, and it only works when r is in between negative 1 and 1. And if you already have this guy memorized, you can just say, oh, that's right. Anything between 1 and negative 1 raised to higher powers is 0. And we call it convergent or converging to this infinite sum. And so when you guys see this example, and it says, find the sum, not the partial sum, the sum, the entire sum. And when the top bound is infinity, you can't plug in infinity, but you can look ahead and say, is this one of those stabilizing ones? Convergent ones? Or is this one of those where it's just going to keep on getting bigger and bigger and bigger and never get closer and closer, stabilizing to a sum? You guys know what I mean by stabilize, right? Stabilizes, there's still some variation, but what's going on? Slowly, right? Slowly becoming stable. That's kind of what the numbers are doing, but only when r is in between negative 1 and 1. Now, some of you can look at this and say, of course it's geometric, and of course there's a common ratio, and the common ratio is. That's good. For those of you that can't, we plug in stuff until we figure it out. Plug in 0. Anything to the 0 power is 1. And careful, to the 0 power is 1, but what is that 1 being multiplied by? 4 is not to the 0, that guy is. So 4 times 1 is 4. What's the next guy going to be? And it's going to be 4 times 2/10, 1/5, so 4/5. The next one will be 4/5 times 1/5, so 4/25. We keep going, but pretty quickly, hopefully you see, oh, it is geometric because every time you're multiplying by an extra 1/5 or an extra 0.2. So here's my question. Convergent or divergent? If r is equal to 0.2, look at your conditions. If r is equal to 0.2, yeah, does that make sense? So we could say, oh, hey, this big old nasty infinite sum, I can just take the limit, or think about the limit as I plug into my s sub n formula, which is one I have to memorize anyway. A sub 1, I already know that he's 4, based on what I can see, times 1 minus, who's my r? 0.2 to the n, all over 1 minus 0.2. Technically, if this was calculus, I would get really stern right now, because a limit as n goes to infinity needs to maintain that meaning as you move on. So the limit hasn't been taken yet. I need to write it again. The limit hasn't been taken yet. But now the limit says, go look at this guy and say, hey, what's he going to do? Well, guys, what's he going to do? If I keep on raising 0.2 to higher and higher and higher powers, it's going to go to 0. And when it goes to 0, in essence, I get the exact same thing as if I memorize this formula for the infinite sum when possible. I get to the exact same place as I would if I memorize this formula as the infinite sum when possible. And I get 1 over 1 minus. Now some of you are like, calculator. No, not calculator. This one's a by hand one all the way, because 1 minus 0.2, that's 1 minus 1/5. And 1 minus 1/5 is 4/5. And when dividing by a fraction, you multiply by the reciprocal, you end up with 5. So if you plug this into your calculator with a 10, then with a 50, then with a 100, then with 1,000, then with a, eventually it'll stabilize to 5. Not because it ever actually hits 5, but because it's going to be 5.00000, and your calculator's like good enough 5. It rounds it, because your calculator can only hold in so many digits. So infinite sum converges, stabilizes to 5. So how would you guys set up number 80? Your turn. I've been talking a lot. Voice is tired. You got to help me out. What should we do? Oh, come on. You got to help me out. It creates what? Yeah, we could put it in summation notation. Find the ratio. That's a good idea. Can anybody tell what the ratio is? Is it 5/6 or is it 6/5? Well, the denominator is divided by 6. Would it make sense if it was this way? Because look, times 6 would cancel, right? And divided by 5 would cancel. Now, if you don't like that, couldn't you have done the... It's nasty. But if you had done it, dividing by a fraction, it's multiplying by the reciprocal, you would have gotten 1 and 6, 1 and 5. Wait, something's wrong. Good. Why do I need the negative? Because the math shows it. Good, and the sign's alternating. So kiddos, look at this. If it's times negative 6/5, if my r is negative 6/5, all right, let's go plug it into that formula. Need to find the infinite sum, the limit as n goes to infinity, of a sub 1, negative 125 over 36, times 1 minus r. Don't change it to a plus, because that r needs to go back and forth and back and forth. The n all over 1 minus. All right, you guys tell me. What happens as I raise this ratio to higher and higher? N needs to get bigger and bigger to higher and higher powers. What happens? It will get bigger and bigger. Now it's going to get like bigger positive, bigger negative, bigger positive, bigger negative. It can't even make up its mind. It's going back and forth, bouncing around. Why did Rachel say bigger though? Why not smaller like this one? Because it's bigger than 1. Well, bigger than -1. But yeah, the magnitude's bigger than 1. Wait, so if this one's going to get bigger and bigger and bigger, it's not going to 0. It's going to like positive, negative, infinity, and can't even figure out which. Is there an answer to this? We could have, as soon as we saw if it's in this category, we could have said no sum. And as a description, we could say, because it's divergent. Did we even have to do any of this work? Not really, because as soon as you see this, for an infinite sum, ... no ending, we say now we're done. So how can you see an infinite sum? The top bound is infinity, like the first example. The top bound is infinity, or ... with no ending. With that, kiddos, section, that'll be homework help. We'll see how you do. Section 9.3 due tomorrow. Seniors, don't forget your extended lunch. Breakfast for lunch. You go straight to the senior patio, and then you guys get an extra 15 minutes at the end. Does that make sense?